Consider the piecewise function f of x equals 1 when x is rational, -1 when x is irrational. Prove that f of x has no limit anywhere. So the very first thing we want to do here before we try to prove anything is we want to understand just what the heck does f of x equals 1 when x is rational, -1 when x is irrational mean. So, well, first off we need to remember, what does it mean for a number to be rational? A number is rational when it can be put as some a over b, where a and b are integers. That's what it means for a number to be rational. A number is irrational when it can't be expressed as a rational. So a rational means any decimal number that has a fixed length to it. Also decimals that wind up having repeating patterns, but will actually be enough with just a fixed length to understand what's going on here. So, 2.000000001 stop is a rational number. An irrational number is a decimal number, or something that can be expressed as a decimal number, where the decimals continue going on forever, they never establish a single pattern, and they just constantly are changing forever and ever and ever. For example, pi, 3.14152 blah blah blah, well, not 2, anyway, 3.1415 blah 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 blah, stuff going on forever. Square root of 2, e, we've seen some irrational numbers that are pretty important, but they're also everywhere total, right? Imagine we had that rational at 2.000000001, but we could also have an irrational that's right next to it practically. It's 2.0000001, and then a random string forever and ever, like 1, 5, 8, 2, 3, 4, 6, 7, 1, 1, 1, 1, 5, 8, 3, 3, like it just keeps changing and changing and changing. So we can have an irrational number right next to any rational number, right? We can get as close as we want to any irrational number. And we can get as close as we want to any irrational with a rational by just putting as many decimals as we want and then stopping at a certain point. So the rationals and the irrationals are right next to each other everywhere total, right? Every single place on the number line has a rational and then an irrational effectively like infinitely close to it. And then a rational right next to that and an irrational right next to that. Everything's just infinitely mashed together. 2 isn't both a rational and an irrational. 2 is simply rational. But right next to it is an irrational, right? You can get as close to as you want with 2.0000000 random pattern. And then you can get as close as you want to 2.0000000 random pattern with a rational like 2.0000000 stop, right? Matching the random pattern, 2.00000 match the first 50,000 digits of the random pattern and then stop, and that's still going to be a rational number because it's technically an integer divided by an integer, right? It'll be a large integer divided by a large power of 10, but it's still technically an integer over an integer, so it's going to be a rational number. So what that means is rationals and irrationals are right next to each other everywhere. So if we tried to graph this, what would f of x wind up looking like? Well, we'd wind up having something that looked like this, where let's say we use blue when x is rational. So we're going to wind up having everything that winds up being irrational will wind up coming out at 1, right? So there's always going to be points, but between any point and the next point over, it's going to wind up having a little tiny hole for the irrationals. And where do the irrationals show up? Well, they show up at -1. So we wind up having the same thing here, and so down below them are our irrationals. And so there's a bunch of irrationals. There's infinitely many irrationals down there. There's infinitely many rationals up here. And they both just are right next to each other, right? You're constantly jumping back and forth and back and forth and back and forth and back and forth if we were trying to plot this thing out, right? It's certainly not continuous because it's two things simultaneously. So why can't we have a limit? Now let's try to think about why will there be no limit anywhere? Well, consider if we tried to talk about some location C, then that means that location C would have to be in either the top or the bottom. And if it wound up being in either the top or the bottom, let's just say the top for argument's sake, then that means we can put some epsilon boundary that is small enough to contain just one of these, right? We make epsilon equal to a half or something, so it can just contain one of these strings, one of these height strings, one of these lines. So since it can only contain one of these lines, no matter what delta we wind up choosing, right? We choose any delta, then we're going to wind up having points that are both on the bottom and the top. So if we were in the top, we can make epsilon only contain the top, but whatever delta size we choose, since the rationals and the irrationals are right next to each other, if we have some rationals, we have to have some irrationals with it as well. If we have some irrationals, we have to have some rationals with it as well, right? Whatever, if you catch this stuff, it's got both types no matter what, if you take any interval chunk of it. So since delta will always produce some interval chunk, it has to have both rationals and irrationals in that interval chunk. So we grab a chunk and it's going to have both the top and the bottom, even though we've restricted our epsilon to only contain either the top or the bottom. And this is the idea of why there can be no limit anywhere, is because we can always choose an epsilon that's going to only take either the top or the bottom line, but no matter what delta we wind up choosing, we're going to have to be in both the top and the bottom lines, so we won't be stuck just inside of that epsilon. It will fail to wind up being a limit, to having a limit. So if we're going to actually prove this formally, that'll be a little bit difficult, but understanding the idea, that's 90% of the battle. I would much prefer that you understand this idea and the proof doesn't make sense, than you really, really work hard through the proof and have a vague understanding of doing the proof, but you don't understand the idea of the limit. At this point, the most important thing by far, and probably ever, the most important thing by far is understanding the general idea and having a sense of what's going on rather than being able to do the specific mechanics. The specific mechanics can always come later. Understanding the idea, that's gold. All right, but let's work through those specific mechanics. Okay, proof by contradiction. So how do we show this? We will show that assume it is possible, and then we will see that if we were to assume it is impossible, crazy impossible things will occur. That if this were true, that we did have a limit, then it won't work. It just doesn't make any sense, and so we will have contradicted it, and we will know that it must be the case that the limit cannot exist. So what we do, we begin by assuming. There will be a lot of writing for this, I'm sorry. Assume there exists. So assume there exists some limit that as x goes to c, our f of x is equal to some value of L. Then, for any epsilon greater than 0, by the definition of how a limit works, we know there exists some delta greater than 0 such that, and from here on out when I write such that, I will probably just use s dot t if I have to write that again, such that for any 0 less than the absolute value of x minus c less than delta, that is to say a x that is less than delta distance away from whatever our c happens to be, we know it must be the case that the absolute value of f of x minus L, that is the distance between the f of x that gets mapped from that x, and L, what our limit goes to, has to be less than epsilon. So that has to be true. Right? That's what it means for it to have a limit. If there exists a limit, then it must be that for any epsilon greater than 0, there will always exist a delta greater than 0, such that if x is within delta of c, f of x must be within epsilon of L. That's what the formal definition is. Now, let us consider. Let me actually change colors, because now we're sort of changing ideas. That was the setup to this thing. So the next thing is consider epsilon equals 1/2. So let's consider epsilon equals 1/2. So therefore, there must exist, by this thing up here, for any epsilon greater than 0, there exists delta greater than 0. There exists delta greater than 0 such that it does this thing here. So there exists delta greater than 0 such that it follows this idea right here. Okay, now let's continue to talk about this epsilon equal to 1/2. So this epsilon equal to 1/2, notice, by the absolute value of f of x minus L being less than epsilon, we have, so notice that the absolute value of f of x minus L being less than 1/2 must be either, well, what are the possible values that can come out of f of x? 1 and -1. So it must be either the absolute value of 1 minus L is less than 1/2, or the absolute value of -1 minus L is less than 1/2. The distance that our f of x is from L must be less than 1/2. So either 1 minus L is less than 1/2 or -1 minus L is less than 1/2. That's what absolute value of f of x minus L less than 1/2 has to come out meaning. But also notice, so furthermore, so only one of these can be true. Right? So these two ideas right here, absolute value of 1 of minus L is less than 1/2, and -1 minus L is less than 1/2, they can't both be true, because if our L is within 1/2 of -1, it can't possibly also reach to being 1/2 of 1. And if our L is within 1/2 of 1, it can't possibly also be within 1/2 of -1, right? It has to pick one of the two bands. Our L can't be 1/2 away from both bands because 1 and -1 are 2 apart. So if you are within one of them, you can't be near both of them, right? So it can't be near both of them. So only one of these can be true. So only one can be true. We're going to use that fact very soon. Only one can be true. Now we go on to say, well, there existed some delta greater than 0 such that it made 0 is less than the absolute value of x minus c less than delta, means that absolute value of f of x minus L is less than epsilon. So by our delta, we know that 0 is less than x minus c, which is less than delta, and that winds up having to mean that the absolute value of f of x minus L has to be less than our 1/2, right? This thing right here. We know that our delta has to wind up making our f of x within 1/2 of L, since we set our epsilon as 1/2. But 0 is less than x absolute value of x minus c is less than delta. That is to say, x is within delta of c must contain rational and irrational x. Right? Since we know that delta has to be greater than 0, and our x is within delta of c, it's within some interval of x minus c to x plus c, right? We know that x is going to be, c minus delta. So it's going to be within the interval c minus delta to c plus delta. Well, any interval, because remember, rationals and irrationals are right on top of each other. Then that means our interval, this interval here, the one set up by 0 is less than the absolute value of x minus c, which is less than delta, must contain both rational and irrational x values. So if it contains both rational and irrational x values, we know our f of x, because it has to be true for any x in this interval, and since we contain both rational and irrational, we now have 1 and -1 popping out of our f of x. So thus, the absolute value of 1 minus L is less than 1/2, and the absolute value of -1 minus L is less than 1/2 must be true simultaneously. Because we know that within our delta bound, we know we're going to have both rational and irrationals, and anything within that delta bound, by the definition, for any epsilon greater than 0, there exists delta greater than 0, such that if you're contained within that boundary of delta, it must map within that boundary of epsilon. So we know we're contained within that boundary of delta, we're contained within c minus delta to c plus delta, but there's going to be rational and irrationals in there, so that means it has to contain our epsilon boundary must contain both 1 and -1. So the absolute value of 1 minus L must be less than 1/2, and the absolute value of -1 minus L must be less than 1/2. But only one can be true, right? This and this are mutually exclusive, because you can't be in both bands at once if the band can only be a total distance of 1 wide around +1 or around -1, right? 1/2 down, 1/2 up, they don't manage to reach each other. They can't reach across, so you can't wind up being in both bands at once with that epsilon of 1/2. So it says that they must be true simultaneously, but we know that only one can be true. So since only one can be true, and we know that they have to be true simultaneously, those are impossible statements to be true at the same time. We have a contradiction. There's a contradiction in our logic. And because we know everything else in our logic was flawless except for our assumption that there existed some limit, we know, therefore, no delta can exist that will satisfy epsilon equal to 1/2, so no limit can exist. And we have completed our proof. All right, I think that's really cool. It's not for everyone, but I think is so beautiful. So I hope you enjoyed it. I hope you got a cool sense of this. And remember, what we talked about here is not something that is necessary for virtually any students. Certainly no student currently at a pre-calculus level. If you're just in the level of this course, you don't need to know this stuff. I'm honest. I won't have to use this stuff at all. It's going to maybe wind up showing up when you take calculus, but probably not even then. It's really something that you only need if you're getting into advanced math. However, I think this stuff is so cool, and there's no reason that if you wind up liking this stuff, it's like going and checking out art for me. If you wind up liking this stuff, you might as well check it out anytime that you wind up being able to enjoy it. It's really cool stuff. It gets your brain thinking in all these totally new ways, and you can wind up exploring this stuff for years and years and years. You can make an entire career out of exploring this stuff. If you think this is kind of cool, you can study mathematics in college, go on to really become a mathematician and just study math for the rest of your life. There's a whole bunch of other stuff to explore. Math is really, really cool. All right, see you at Educator.com later. Bye.